Good afternoon, everybody, and welcome to you all, and thank you for joining us to celebrate National Science Week. I'm Professor Sharon Green, and I'm Deputy Head at the National Centre for Food Manufacturing, and we're based at Holbeach in South Lincolnshire, and we're part of the University of Lincoln. And I'm joined this afternoon by my colleagues Oliver Horn and Dr. Mohammed, and we want to be able to share with you a few examples of how your food is made. So the food and drink industries are part of a really long supply chain linked to farming, growing, through to food processing, manufacturing, and finally to the sale of food in supermarkets and restaurants. So we rely on scientists, technologists, engineers to support us, and maths comes into our everyday lives. So maths helps us on modelling the processes that ensure that food production is safe, that we store it correctly, we test it correctly, we go through transportation, cooking, and so on. And finally, how you eat and digest it still involves mathematical equations. So I'd now like to introduce Oliver, who's going to talk about extrusion technology within food manufacturing.
Good morning, everyone. So extrusion is the process of forcing a material through a die at a set shape to produce a product. So like pasta, for example. There's many different types of extrusion in industry. Extrusion can go from making plastics to pasta to cereals to crisps. I'm just going to play a short video now of our extruder in the factory running, and I'll just talk you through how it works. So this is the material hopper, and what you'll usually put in is a flour or starch mix with fibre or protein. That goes down through into this barrel, which you can see in the mirror in the middle, and in there are a set of twin screws. The screws are an Archimedes screw shape which force the material mixed with water through the die at the end, and in the middle it's cooked. So you see the sludge coming out the end. That's where we're just starting up the machine, and now we're getting a more firm product. The material is pulled to sort of flatten out and make it have an even shape. It's essentially like pasta. And oh, sorry, can you hear me? Yeah.
Yes.
And you can see there we're laying it out on the table to dry. Usually, if you were making pasta in industry, for example, you would have a die face cutter, which would cut at a set interval, which would make the shapes a certain length. We don't have one of those because this is a test kit, so we have to make long strips and then cut them individually. You can see here what I'm doing is checking the moisture content of the product. This is really important because the extrudate we call it an extrudate when it comes out, has to be at 28% moisture to be a good usable product. If we find out from the moisture content that it's more than that, we'll has more moisture than that, we can increase the feed speed, so put more flour in. If it's got less moisture, we can increase the water flow until we get our optimum. So you can see there I'm pulling out the extrudate, and that will be then left to dry once we've got the optimum moisture content. And the moisture content is really, really important because of the next step in the process where we actually use this product and expand it into a snack. We'll just take you over to the moisture content here. So the moisture meter works by heating the product until all the moisture is cooked off. That way we know the weight of the dry matter and the weight of the moisture that came off. Once we've got that, we can then modify our process to make it correct. You can see here it's going up to 23, and as I said before, it needs to go up to 28 before we're happy with it. Once we've finished that and we've cut up into small pellets, we'll then dry this product in the oven to a moisture content of 13%. When it's 13%, it's reached an equilibrium, which means it can be stored in air without gaining or losing any moisture. This is really important for keeping the product stable, because if it's at 13% moisture, it's not taking any moisture on, so it won't get moldy, and it's not losing any moisture either. It's a stable product, which is really good. And that product can then be sent off to factories, be processed into snacks. Snacks that do this are, for example, quavers, or the multigrain waves you can get. This is a extruded snack that's dried and then it will be expanded. The expansion process works by getting our 13% extrudate and heating it up really fast. So the moisture particles in the cells expand and they sort of blow up into a sort of crispy shell of a product. Products that do this are quavers, the little bacon rashers and the multigrain waves. All sorts of products do this. That's called a third generation snack, where we've got the product, made it, dried it, and expanded it. We've also got second generation snacks, which are products that are expanded at the extruder die phase. So you see where it comes out of the extruder, some products will expand there. So products such as Wotsits will come out expanded because all they've done is they've had the end of the extruder very, very hot to put that expansion process right there on the extruder. And then you've got first generation snacks, which are, so for example, Rice Krispies, because you've got a product, you heat it up, expand it, and that is an expanded snack. Popcorn is another first generation expanded snack. You see there, we're drying the product in the oven. It's really important during that process to keep the oven at a set temperature, because if it's higher, they can actually expand in the oven. I've got here an example, you can see my screen now, of this is a dried extrudate, and this is after expansion. So you can see the little bubbles on it, and it's crispy, dry snack. This will then need to be stored in an airtight container because it's got low moisture content, because all the moisture's gone off from expansion, which means it will then be suitable for eating. Whereas these can be stored without being airtight and shipped around to factories to be sold, which is an advantage of these third generation extruded snacks. So once we've made this snack, there's various tests we'll do on it to verify it's a good product. So we'll do a texture analyzer test, where we'll have a machine that's got a probe that goes down, and it will crush one of the extrudates and tell us the crispness, the firmness, and the toughness, and that gives a profile of the product. Another test we'll do is a basic sensory test. We'll have a panel of people to come and taste the product and tell us what they think about it. So there's all sorts of things that go into just making a small snack. But the extruder can make loads of different snacks in many different ways. The screws in the extruder I've got here, and these can also be modified to produce a different snack. So these turn round as a twin screw extruder, and they've got different sections that do different things. This first section just pushes the product along. You've then got these sections, which are kneading blocks, which work the extrudate into a sort of plasticky substance. And here, right at the end, you've got a really thin set of screws which force the product out through the die. There's many different dies you can have. Think about your spiral pastas, which will have a spiral shape. We usually just use a basic slit die because we're doing it for testing. But yeah, there's all sorts you can do with it, and there's many amazing products you can make. Most cereals are extruded. You think of a lot of pet food as well. There's so many different extruded products out there, and yeah, that's extrusion really. Is there any questions?
Brilliant. I've got loads of questions, Oliver. So when you showed us the first product, when it was dry, and then you showed us the other one, you've got them both there with you at the moment, and you've got one that's gone puffy. When we open a bag of quavers or Wotsits, for example, and we get a bit that's a bit hard and it doesn't look like the rest of it, is that because it hasn't blown up when you've done the process after extrusion?
That's correct. And I've actually done that myself here. You probably can't see, but right at the edge, it's not expanded because they all take different times to expand. If you've got a thick product, so say if you've got some of the thin, some are fat, it will take longer for the bigger ones to expand. So you're going to get some that don't work all the time. And it also depends on how they expand them. So there's different methods. You can bake products, you can deep fat fry them, you can use a microwave. I used a microwave this morning for these, and it's very easy. You just get a very uniform product. But quavers, for example, I think they're deep fat fried. And one issue you can get from that is that not all of them go under into the oil. So the ones that are hard, like you say, probably didn't get properly deep fat fried. Baking is the main method these days because people are very health conscious.
Yeah. And you mentioned something earlier about first, second and third generation extrusion. So what's the benefits of third generation extrusion in food manufacturing?
So what you get when you make a third generation extruded snack is a product that's stable and you can keep it for a long, long time. It's not going to go off and you can sell it in bulk and it's very easy to store. Whereas if you were to make a third generation snack that was expanded on the extruder, like a What's-It, that has to be bagged in an airtight container and pretty much sold as is. And you can't store them for a long period of time because they'll gain moisture and go stale. Third generation snacks are really good, but you can't extrude them because then they wouldn't be a first generation snack.
Yeah. So things like pasta can be in the bags in supermarkets for quite a long time until their best before date comes up because they're dry, they've been extruded, and everything that you've explained to us today is why they can keep so long in the packs that we see them in.
Exactly. And another thing is I was talking about the moisture content. Say if we hadn't dried the moisture content to the correct percentage, that bag of pasta on the shelf would go moldy, even if it was just 1% more moisture. So that's why the moisture content is really crucial. And if, for example, we hadn't got the extrudate to 28% moisture as it came out, when we cut it up, it would have all stuck together in a big gloopy ball. That's another factor.
Okay. And so when you think about things like you mentioned cereal production earlier, instead of crisp production, what generation is that then?
That could be either as well. Trying to think of an example of an extruded cereal.
Well, you mentioned Rice Krispies earlier.
Rice Krispies are first generation, so they're not extruded. But most will be a third generation snack extruded because you don't really get anything like What's-Its, for example, in your cereal. But a lot of them are baked products. You don't often get any deep fat fried ones, unfortunately.
Okay.
I just thought of one actually. Do you know those ones? I think they're called Crave, and they've got a chocolate filling.
Middle.
Because the extruder can do that as well. Some extruders in industry will have, they'll be able to extrude the outside and pump in a sauce in the middle of the extrudate, seal it up, and then that will then be expanded elsewhere. So that's another thing that extruders can do.
And that's how you get the chocolate inside the pillow.
Yeah, and those extruders in industry will be absolutely massive, even though they're making small things. Ours is a tiny extruder. You'll never see one smaller than ours. These screws in industry would be probably about that big, and the actual extruder would be the same size as this room.
Okay, and I've just got one final question for you, Oliver. What ingredients are the best for expansion in this sort of technology?
It depends what you're making, but if you are making a crisp type snack, I find that potato starch is very good for expansion. Stuff like maize starch is good because it gives this is actually a maize starch product, and it gives this sort of yellow appearance. It's good to do a mix. So if I did a mix of maize and potato, you get a nice yellow appearance with a big expansion. More starch is more big bubbles, but you could add protein and fiber to sort of stop the expansion if you wanted to limit it in a certain way. So these recipes for all the snacks are really mathematically formulated to give the correct snacks. You think of a Monster Munch, for example, how much formulation has got involved to thinking about what the ingredients do in those snacks. They're mainly maize, you can tell by the colour, but they will have had a lot of potato starch for that big expansion as well.
And when you've done products that are the snacks like Quavers and Wotsits, they'll then go through a separate process to get the coatings on to give them the flavours that we know. So you can get your hot and spicy or your salt and vinegar, and then that's the next process after the extruded process has taken place. Is that right?
That's right, yeah. So some will add flavour to the material going into the extruder, but often what you'll get is it's essentially like a big barrel. The crisps go in and they're tossed around in the big barrel, and flavour powder is trickled in at the top, and they're tumbled along with the flavour, and then they'll be baked or deep fat fried, or they might have already been baked or deep fat fried depending on the recipe.
Well, that is really fascinating. Thank you ever so much, Oliver. And perhaps you'll pop off and make us some more Quavers now for this afternoon.
Get the deep fat fryer on.
Thank you. And now I'm going to introduce Dr. Mohammed, and I believe you're going to talk to us about robotics in the food and drink industry.
Hello everyone. Thank you so much, Sharon. Yeah, my name is Mohammed Al-Fadli. I obtained my PhD from the University of Nottingham in 2018, and I joined the University of Lincoln in 2019, and I do the robotic research at NCFM. And today I will be presenting about the robotics in food industry. Okay, so I'll start by overview here. So in food industry, we have like 3 stages, and the first one is the primary processing, which is like cleaning, sorting, inspection. While for the for the secondary processing, we have blending, cooking, for example, and for the end of line, we have the packaging and product casing. Do you hear me well, Sharon?
Yes, that's fine. Thank you, Mohammed. We can hear you.
Yeah, fantastic. Okay, for the first stage, it is like fully to semi-automated, while the second one is it's fully automated, so we need to improve it in the food industry. While the last one, it is highly automated because the automotive industry, so we can use that, but how we integrate it with ours. Okay, so and we have challenges in food industry, and we can classify them like the bin picking because fruits and etc. they are soft, so we have challenge to pick them. So we use soft and vacuum clippers or touchless actuators. While for there is another challenge which we call it like advanced sensing, and for that we use machine learning, machine vision, and also chemical sensors. Okay, so another challenge we have the non-solid manipulation, and for that, so like ingredients, for example, starch, for example, and for that we use advanced controlling methods and machine learning. Okay, and we have another challenge which is we call it like dexterity for making like food, like sandwich, for example. Okay, so for that we use also advanced control methods and machine vision we can use for that.
So on those, Mohammed, that first slide you showed us where it's got a piece of equipment that can do that, we already have the technology in the food and drink industry to be able to pick things up with very gentle finger-like robots that can do that.
Yeah, cool. Yeah, so we have the soft actuators, and even we have touchless actuators, which is useful for that. Yeah.
And can they pick soft things up like fruit, for example?
Yeah, with for example, this soft grabber, we can pick the soft fruit as well. Yeah.
And what sort of things would we use things like machine vision technology for in the food and drink industry?
Okay, so we can use it for the quality control in that sense, and also to locate like where's the fruit, where are they are, and then we can go for them. The robotic arms can pick them. Yeah.
So if we had a pizza going down a production line and it had a piece of burnt base on it, the vision sensor would be able to pick that up, would it?
Yeah, of course. Yeah, it can like with the vision on the machine learning, so we can like pick and find any defects as well, and then we can like also find what we want. Yeah.
Brilliant, thank you. And I think on the next slide you showed us some other different types of robots, didn't you?
Yeah, you mean this?
Yeah, so that one on the right hand side, is that a mixing robot?
Okay, so the upper one, in the upper corner,
Yes.
it is like to manipulate the ingredients, and for example, we use that technology for weighing the ingredients. Yeah, and while the second one we use it like for chilling and for the like food assembly, for example, we can use that. Yeah, like all the process. Yeah.
And which ones of these are you working on at the moment, Dr. Mohammed?
Okay, thank you so much. I work on this one, non-solid manipulation, for the weighing of the ingredients, and I'll show you a project like in the other slide. Yeah.
Okay.
About that. Yeah. Okay, so I continue like when the robot can work like nearby the human or with the human, so we need to be careful for the safety and the hygienic design and and for the easy interaction. So we need to sort these challenges. Yeah. While the warehouse, like the end of line, it is already highly automated because it is already like developed in the other industries, like the automotive. But how we integrate all the stages with this? Yeah. Okay. So this is one of the projects I'm working on, which is non-solid manipulation project. So for that, I use like a rigid grabber to attach to the buckets. Okay, and I use a scale, if you see here, to measure what is already there. It's like tipped, and then to give me feedback. Okay, and I use like control system for controlling the motions of the robot and also to monitor the scale. Okay, and the last thing is the safety. When there is a human nearby, the system can stop or for making a safe interaction. Yeah.
So this robot that you're working with, Mohammed, it's a bit like working on on a gaming technology, is it?
Yeah. So like I use like in these like in the I use Python to program that. It is somehow like it's related. Yeah. Okay. So here's the control system. Okay. So if you see, sorry, it is like a bit technical. Yeah, maybe some are interested in. So I have two loops. If we see, it's kind of two loops or two controllers. One of them, it is the first one to control the motion of the robot, while the second one is to monitor the scale. So these are like two loops or two controllers in one control system. And also I can like get rid of the scale, and I use like artificial intelligence to estimate. So I can like use the robot without the scale. And I show that in the demonstration now. Yeah, so hopefully the quality is good. So here is a demo. So here is with the scale, and this one without scale. So I can lift, and then so the robot, like I trained the robot to do this task of doing the weighing. Yeah, I wanted like 300 grams, and hopefully you can see, it's like 300 grams. So this is with the scale and without the scale. The second one is artificial intelligence. Okay, so, and here's like some trials, like I have different targets, like 200 grams, 300, 600, and then I do different experiments. And again, like the accuracy is like at most like 1%, the error, which is like kind of 99, which is very good. 98. Okay, so this is the evaluation of the project. Okay, and there is another one, which is we had a demo about a soft, like this has a soft hand kind of to do a cup of coffee, and also to interact with the human in safe way. Let's see. I run it. So here is the interaction. So you see the robot like human hand. And here's the coffee powder. Sorry, I think it's, so this is like a demonstration for the coffee, and here is a robot can do more. This is from last month. This robot showing like flowers for the big robot. Okay, and thanks so much for.
And so really that robot that you've been showing us, Mohammed, is very much like a human arm, isn't it? So the ways that it's moving, you've managed to train that. And if you look at the different bits, it's really like an elbow and a shoulder on somebody's arm.
Exactly. And even its motions, like how it behaves.
So do you get the robot to make you cups of coffee every day? Or you could do.
I can do.
And you mentioned earlier about that the robots are working with humans in a very safe way. How do they know how to work safely with humans?
Okay, so if I show you this here, so it is, you see how it is. So I roll and and also it can interact like human hand. If you saw in the video, and also if it is collide with the human, it's stop as well.
Okay. So we use robots already in the food and drink industry. In the next 10 years, for example, how much more do you think we'll see robotics and automation coming into the sector?
I believe like it will like work hand by hand with the workers. So it can help them, especially like nowadays in COVID, and there is a limited, like people can't be inside one space. So like robot can be working with them as well.
So we need so many more engineers to come into the food and drink industry, because without the knowledge that people like you have, we can't bring these technologies in at the pace that we need to, because working in the food industry isn't necessarily just standing packing on a line because there's robots and there's really exciting things happening, but we need the skills of the future generation to come and help doctors like you develop these sorts of technologies.
And as well, automation and robotics in food industry is relatively new, and it has its own challenges, the food industry. So we still have like a long way to do like all this advanced like automation and helping other workers.
But in
So
our lifetime, we will see those huge changes take place, won't we?
yeah, of course. Yeah,
And how much?
especially there is machine learning advance. It's like advancing. So yeah, so I believe the advances in food industry will be like faster or like in a few years.
And how much do you use maths when you're working on your robots?
Oh yeah, so much math I use. For example, I can show you the control system. Yeah, for this one, and I had like math. For example, like this stage. So for example, we move our hand because it's processed in the brain. But for the robot, we need math, how we move the arm, and also how we calculate, for example, in this project, the target weights and the current weights. So we do math, like lots of math. It's really important, the math.
So maths can be fun.
Of course, yeah, of course, and it's very essential.
Yeah, brilliant. Thank you so much, Dr. Mohammed, and thank you so much to Ollie for this afternoon and showing us just a little insight into how we use engineering and maths in the food and drink industry, and Ollie particularly as well for showing us how perhaps some of those cereals and snack products are produced that we all enjoy as consumers. So thank you so much for joining us this afternoon, and stay safe, everybody, and thank you